on series, and basically we're going to have weeks and weeks of finding out if a series converges or if a series diverges. When we say a series converges, what we mean is that if you add up all of these terms, there is a number that they add up to, right? There's a limit that they add up to. That's what convergence means. Diverges typically means that if you add all these numbers up, right, the value of the function at 1 and 2 and 3, it becomes infinite, but it can also mean it bounces between two answers as well. We just call all of those situations diverges. So we're going to look at a filter called the integral test. And basically it says the following. You'll notice there's a little change to the notation because the way this test works, it kind of is helpful to write that notation. You know, when I write down a series, I might write it something like this: n equals 1 to infinity, 10 over n squared, right? This guy here, I would typically have written last week at least. I would have said, an would have been 10 over n squared, right? I mean, so that's the notation. But it's okay to use this notation. And I want you to think of an as just being the exact same thing as f of n. But the reason why this notation works is because of what comes later. So if you can show me that this expression is positive and decreasing, and you must do this or you haven't done the whole test. Even though in the homework, they don't force you to do anything, because at the end of the day, the homework questions are going to be dead easy. A lot of the questions in the homework are just going to have two choices, especially the first half. So if it converges, you pick that one and you're done. If it diverges, you pick that one and you're done. And you get 5 guesses. So I guess if you want to just not learn anything, can you just say, pick the first one if it's wrong, pick the second one. Pick the first one if it's right, great. Pick the first one. You could do it in 2 minutes. You could do half your homework and learn absolutely big fat zero. And when I do the midterm, you'll know absolutely nothing about how to do this, and you will bomb that midterm in the final like nobody's business. So the bottom line here is, don't do it. I know it's going to take you a lot of time and a lot of work, but that's your practice. If you don't take time and work on something, you won't remember it, right? Watching me do it twice is not the same as you doing it 10 times. It just isn't. Much as I might like it to be true for you, it's not. So anyway, back to the thing. You have to prove that this f of n, this function, is decreasing and positive. And then you do this. This is actually all about integrating. You integrate from 1 to infinity the f of x. If this thing is a number like 42, the series converges. Or you find the integral and the answer is the limit's infinite, right? It diverges, right? It doesn't exist. If it is, then the series. So essentially, this integral and this series behave the same way, right? If this converges, that will converge. If this diverges, that will diverge. So that's the process. Prove to me it's positive and decreasing, and then find this integral. And depending on what you get from this, you'll either make a conclusion that it converges or it diverges. Are we good? So let's jump right in and show you an example of that test being used. Let's show you a converging one, and then I'll do a diverging one right after it. And I'm picking nice simple ones to start with so that we can just get used to the process. So I would like to know, does that series converge or does it diverge? That's our question. So that means that the function f of n is 4 over n squared, right? So first thing is, I want to prove it's positive. Some of the proof are kind of trivial. Would you agree that as long as n is 1 or bigger, isn't 4 over n squared positive? I mean, there's no algebra to prove it. So I'm just going to stick that down and say it's obvious. Would you agree? 4 over n squared is positive, and it will be for almost every question you're going to do. Proving it's positive is trivial. I don't expect you to do a great deal. Proving it's decreasing, on the other hand, does require work. Here is the guy that we're dealing with. I'm going to call him that guy. I am going to differentiate him. If a function is decreasing, what can you tell me about its derivative? Is it positive or is it negative, or does that not matter? If a function is decreasing, what can you tell me about its derivative?
It would be negative.
Right, so what you're going to do is you're going to prove that the derivative of this thing is negative. So the first thing you've got to do is differentiate it, right? And then we'll work on proving that it's negative. So, and we're only interested for n greater than or equal to 1, or at least some number bigger than 1. So, power rule, multiply by the power, reduce it by 1. That's a little bit awkward. Style points, return it back to original. Okay. Are you comfortable about that being the derivative? Right, nothing too sneaky going on. Now I'm going to prove that it's negative. Negative 8 is a number that never changes, and it's always negative. The little circle around it is just to emphasize it, right? The top is negative. Would you agree that if n is greater than or equal to 1, would you agree that n cubed is positive? 1 cubed, 2 cubed, 1,000,000 cubed. So the bottom is guaranteed always to be positive, provided that's true. And would you also agree that a negative on the top divided by a positive thing on the bottom, doesn't that give you a negative answer? And negative answers, of course, are less than 0. And so we have now proved it's decreasing. Are you comfortable about the logic that I used to prove that the thing is decreasing? I found its derivative, and then I took it apart and said this bit's plus, this bit's minus, so the whole thing is negative. That means it's decreasing. We're done. So the last part of the puzzle is the step 2 thing. I'm going to find the integral from 1 to infinity of 4 over x squared dx. Now we have to bring out something that you haven't done for a fair amount of time. In Calc 2, can you remember doing indefinite integrals? Integrals were at least 1 or 2. In this case, it's always going to be this form. Well, it depends who you get, but if you did it with me, you would see this. Oh, and while I'm at it, I'm going to rearrange the 4 over x squared to look more like that. Does that ring a bell? You remember that? Make it t and then make t infinite. Right, so here goes. If I end up proving that this thing is infinitely big, doesn't that make the series diverge and we're finished? If I can prove that this is equal to a number like 42, that means this converges. Right? I don't care what number it is, as long as it's a number, that means it converges. Right? I don't care what kind of infinity it is, right? It's going to diverge. So here goes. Add 1 to the power and divide by the new power. Evaluate it, and I shouldn't have done that, it should be a t. Evaluate it at t, x equals 1, if I focus here, to x equals t. Going to do some style points on it. Negative 4 over x, that's a much better version of it. Now I can simply just plug in some numbers, replace the x by 2 different values. When you plug in t, you get negative 4 over t. Take away negative 4 over 1. Well, take away negative 4 over 1 is basically add 4. Are you comfortable with that calculation just done in my head? Now, it depends on what you get here, how easy finding this limit is. But the most common techniques you're going to be using are brute force. That basically means, right, make t infinite, right, and see what you get. Or maybe L'Hopital if this thing is a really ugly expression. Hopefully, most of the time, it's going to just be brute force and you'll be fine, right? You should be able to get away with it. Well, or occasionally, I guess, divide top and bottom by t squared. So I'm going to plug in infinity for t. Would you agree that negative 4 over infinity is just 0. So this thing adds up to a number, right? It converges then, right? If the integral is a number, it converges. So we finish with, by the integral test, this series converges. And that's all you say. Don't say that this adds up to 4. You might be tempted to think, because of all this working and the fact that the integral is 4, that this is equal to 4, right? You know, that's what it adds up to. Like, you know, like in the geometric series, we can actually tell what it's going to add to. All this tells us is that it converges, nothing more. In fact, I could probably tell you that the only thing it won't converge to is 4. It'll either converge to something probably less than 4, right? 3.5, 3.1, right? Or some weird value, but it won't converge to 4. So just in case you got that little extra bit you thought was true. So we've shown that this fella converges. We proved it was positive. We found its derivative and proved that its derivative was negative. That means that the function was decreasing. We found the integral of it from 1 to infinity. We got the answer to that was a number 4, which means it converges, which means then the original series also converges. And that's the logic from start to finish. Are we good? Right. Next fellow I'm going to do is a guy you already know. Can you remember that guy? It's called the harmonic series. If I write them down in full, you remember the one that we kind of talked about, that a lot of people think that it should converge, but it doesn't, right? That one there. Right. I'm going to prove to you that that diverges, right? Because that's what I said, you know, on Friday, or when was it? Thursday, right? That it diverged. So here goes. Would you agree that's trivial? As long as n is greater than or equal to 1, would you agree that 1 over n is positive? I don't really need to do any more than just state the obvious. Now, I'm going to call it n to the power of negative 1. I'm going to differentiate it, which is multiplied by the power, and then divide, and then reduce the power by 1. Can I cut that straight to negative 1 over n squared, or do you need to see the minus 1 into the negative 2 and then turn into that? Are you comfortable with that? Okay. Now, would you agree that negative 1 is always negative? Would you agree that n squared is always positive? So a negative on the top divided by a positive on the bottom means that the derivative is negative, and so we have now proved that it decreases. So that's the preamble. You must prove that the series is positive and decreases before you even attempt the final step. So let's do the final stage then. We're going to find the integral from 1 to infinity of 1 over x dx. That's going to be, the limit as t tends to infinity. 1 to t, 1 over x dx. Okay, what's the integral or antiderivative of 1 over x?
Is that the natural log of absolute value of x, right?
Technically the absolute value, but we'll just call it x because everybody's positive. And now I can substitute in the two guys, and we get the natural log of t, take away the natural log of 1. And again, I should be able to do this one with just brute force. It's going to be the natural log of infinity. Wait a minute, isn't natural log of 1 just 0? So take away 0 is not going to do anything. So the natural log of infinity, would you agree that's infinite? I know it takes a long time to get there, but doesn't it still get there? Right? the log of an infinitely large number is infinite. So that means that our series, by the way, that diverges. So that means our series also diverges. And I should tell people that I'm doing it by the integral test. I think it was on Thursday where I kind of did a pseudo proof, you know, like to prove to you that 1 over n diverges. Can you see now that you've actually got a more formal test called the integral test that does prove that it converges, right? Not that, you know, we believe it should, but this is essentially take it to the bank, you've now proved something. Any questions so far? Right. Going to do a side issue for a little while. Since this technique involves integrating, I'm just going to do some integrals and techniques for integrals, how you would approach them, so that we can, you know, when they happen in the series, we're more used to them. So I'm not going to do the whole thing, you know, 1 to infinity, right? So I won't even put in limits. I'll just do the integral. We've already done that one, but I just want to put it in as a, right? Technically a plus C, but I'm not putting those in either. What technique would you use to integrate if that happened to you?
Substitution.
Correct. What U sub would you use?
U equals x squared.
Okay. Now, based on differentiation, you get 2x, crossover, you get 2x dx, isolate, oops, that's the next, isolate the dx. So what we have here is x sine of u 1 over 2x d of u. So that thing now becomes 1/2 the integral of sine u du. Do you see that would turn out quite nicely, wouldn't it? What technique would you use if you had to integrate something that looked like that?
Substitution.
In fact, would you agree it's almost a carbon copy of the one that we did a moment ago? And can you trust me that that one ends up being 1/2 of 1 over u du? Right, you can fill in the gaps. What technique would you use if you had to do that guy? I'll tell you who he's not. It's not a substitution.
Integration by parts.
Yep. And depends who you get taught by. If you get taught by me, we call this F and we call that G. And if you didn't get taught by me, you might get the UDV people, which is totally fine and that works. So you use whichever technique that you're used to. Now, let's do this fella. Any suggestions for how that would be integrated? That's got you puzzled.
I think it's just you would use a natural log for that.
It is,
Return.
right.
That
You're
or
right.
trig substitution, I think.
Oh God, don't go. Let's have a list of things you do. And right below cut my legs off, then you have trig substitutions. You do not go near a trig substitution unless everything in the world has failed. Because those are do you remember doing them? Half an hour a time.
We did integration by triangle or something, or essentially just set it to Pythagorean theorem, and it made it quicker.
Yes, I know that technique.
Yeah.
Right. Still horrible.
But otherwise evil, yes.
Evil. So just don't do them. And I'm having a quick scan, and I don't think we've got any that need them, right? So you can keep that out of your vocabulary, right? So give me a different technique for this. There are two ways you could do it. Don't overthink it. There are
What
two
about
ways.
the natural log? Because when it turned into the natural log of 4x plus 1 inside, it would be
Yeah.
1/4 the natural log.
There you got it. That's the shortcut. Can't you just basically do it like it was a general? And the other way, which it takes you a little bit longer, is just basically a U sub. Right. So you got to be, because you're going to do integration in every single one of these questions, right? You have to be up to speed on U subs. Memory is a good one. I just thought of this one. I'm calling this one memory. They don't need to do anything at all except have a good memory. What is the integral of 4 over x squared plus 1?
Is that 1 over x squared plus 1? Is it arctan, right?
It is, or as I prefer you to call it, inverse tan. Only Americans call them arctan.
And there should be a 4.
And there is. That's it. Right. Okay. Let's zoom over to the questions. And all I'm going to be asking you here is, for some of them, tell me how you would integrate, right? That's all we're going to be looking at. And can I make this bigger? Because those are kind of tiny. No. Okay. Can I make it bigger by going here then? Right. Are you still looking at question 1 n to the -6? Oh, good. Okay. Then I can make this a little bit bigger because I'm not sure all of you have decent sized screens. Right. If you want to integrate x to -6, would you agree that's just a power rule? Right, add 1 to power, divide by new power. Nothing particularly going on. There's similar to the one I just did with the logs. What would you use in question 3? What method?
That's a U sub, right?
Correct. What would the U sub be?
X cubed plus 1.
Correct. Or n cubed, whatever letter of the alphabet you want, but I would use x. What about question 4?
The integration by parts.
You could, but you'd be making your life a misery. Think of another strategy. I mean, I'm not saying it wouldn't work. It probably would eventually, but I wouldn't want to try it even if it did. Think simple before you think hard.
U substitution.
Yeah. Who would you make as a U sub? You're right.
X to the 5th.
Yeah, or minus x to the 5th, both are fine. That horrible one is just a power rule, isn't it? Who cares what the power is? You just add 1 to the power and divide by new power, right? We can't do that one because we don't have a formula. Oh, this is a really cool question. I might actually do this one if we have time. It looks horrendous, doesn't it? But think simple before you think hard.
Question, is that 3 times square root of n, right? Or 3 to the power of root n?
It's 3 times the square root of n. And it's not very clear, but that's what it is. And the guy in the bottom is 3 times n to the power of 3 halves. You're not sure because it's kind of disproportionate in size. What technique?
Couldn't we use a natural log for that? Because it would just decrease.
No, you got the 1. That kills it.
Yeah.
Okay, what technique? Even if you're not sure, what might it be, or what would you hope it would be?
A U sub.
It is. Do you know who the U sub is?
The bottom expression.
Yeah. Now, it might not look like it's going to work, but trust me, it would work. So sometimes you have to try it and then think, oh God, I never thought that would work. But it's a U sub. Have you noticed how popular power rules and U subs are so far? Right? I think that's been every question virtually. Do you recognize 8? Because 8 is an example of the one I just did. But it's not n squared plus 1, it's what, n squared plus 16. Now this one is also if you've got a good memory, but this is much rarer. So I might return back to here and see if I can remind you what this one is. Put a 1 on the top. And we have this fella. It's 1/4 the inverse tan of x over 4. And if you're wondering where the 4 comes from, it comes from the square root of 16. Does anybody remember seeing that like maybe twice? You know, it's a very rare thing. And if you don't remember it, well, you now remember it for this question. Right. Okay. Let's return back and focus on what techniques we should be using to integrate. 9 is a cool question. And if you get 9, you deserve brownie points. Not that I can give you real points, but you deserve brownie points. Which I don't know, does brownie points mean that you get brownies like in cakes?
Sometimes.
Okay, okay. Virtual brownies then, go for it. What technique?
A U substitution.
It is. But now the key is, who is the user?
Natural log of n.
You nailed it. You get brownie points. Do you know that just turns into 1 over u, which is pretty easy to do. How about this as a rule? Look for a U sub before you do anything else. Even if it doesn't look like an obvious one, go for it. And just to break my rule, question 10 is not a U sub. If
I
it
think
was
IBP, right?
Say again?
Is that integration by part, right?
Yeah, it is, yeah. What about 11 that looks very similar?
I think that is a U subs.
It is. And I think we did one of them ourselves, didn't we? We talked about it. Isn't the U sub, well, I guess we'll have to call it K squared or something, right? Or X squared, right? Even, wasn't that the one you did earlier? Looks like it anyway. There's a really cool question. There's some really good ones here. That's a U sub. But the trick is telling me what the U sub is, because it's not obvious. What U sub in the world it is. And do you know if you do that, I'm not sure what the multiple is, it's a 6, I think. It ends up being 1/6 of 1 over u squared plus 1 or something. So you end up with a 1/6 of an inverse tan. It comes out relatively nice. We're almost finished these. Well, that's not really, these are the special cases because they talk about things. So I think we've finished that part of the story. So it's a case of practice makes perfect. So I'm going to pick some of these guys. Does anybody have any preference on the ones we've got? You don't need to tell me exactly, but say, oh, that one with the 1 over n log n or something, right? Did any have any, ooh, I'd like to see that one. Otherwise, I'm just going to pick a couple on my own. Anybody see ones that, whatever, piqued their interest?
Could we do the one that we just last looked at?
Okay, let's see what that one is. Yes, okay. One of the most difficult ones, but that's fine. Let me kick over to my whiteboard so you can see me write it. This is going to be a version of question 12. we're going to be looking at this fella here. And I have to prove it's positive. Can I just look at that and say, look, if n is greater than or equal to 1, would it be pretty obvious that that is made up of positive numbers, so it's positive, right? Okay, so I'm just going to say greater than 0 because it's obvious. Now I'm going to prove that it's decreasing. I haven't even got to the integration yet. So to prove it's decreasing, I'm going to have to differentiate, and I'm going to have to prove that that derivative is going to be negative as long as n is, say, greater than or equal to a number like 1. Well, it's a quotient rule. Do you see how this class is using Calc 1 stuff, Calc 2 stuff, you know, stuff from, you know, algebra, you know, you name it. Bits and pieces keep popping in and, you know, trig stuff occasionally. So f dash g, take away f of g dashed over g squared. If you differentiate the top, you get 5n to the 4. You leave the bottom alone, you get that. Take away, leave the top guy alone, and differentiate the bottom, which gets me 12n to the 11. Oops. And the whole thing is over n to the 12 plus 1 squared. So I'm going to have to try and prove that that is negative. Well, first thing I'm going to do is multiply out all these pieces. So that's 5n to the 16 plus 5n to the 4, take away 12n to the 16. And that combine, and I now have 5n to the 4, take away, what would that be, 7n to the power of 16. Still over this guy squared. Still good? So, okay. Now, is there anything style points I can do to the top that might make it a little bit prettier? Anything I can do to 5n to the 4, take away 7n to the 16.
You could stick the negative number as a first variable, like a source sum.
Oh, I was hoping you would say take out n to the 4 as a common factor. Would that be a little bit more straightforward? Now, if I did that, I get this, right? Yeah, that's me differentiated it and made it. The lighting here is pretty horrible. Is that very bright for you? Right, let me see if I can fix that with lighting. I think it's because the day there. Does that help? A little bit better. Okay, now I want to prove that's negative. Essentially, the way I'm going to do it is I'm going to say, look, n is greater than or equal to a number like 1. I'm going to look at this in 3 pieces and see what we get. Would you agree that n to the 4 is always positive for any value of n in that range? Agreed? We'll worry about this guy in a minute, but I'll come to him. Would you agree that n to the 12 plus 1 when you square it is positive? Because no matter what it is, if you square it, it's positive. Okay, let's look at the last guy. Would you agree that if n is 1, 21, or 2 billion, would you agree that 5 take away 7n to the 12 ends up being negative? Does the logic of that make sense? 5 take away 7n to the 12 ends up being a negative thing, provided n is 1 or something bigger than 1. So the whole result is it's negative. It is decreasing. Do you see how much time you spend on one question? We're only, what, halfway through, right? We've proved that it's positive and decreasing. What we now need to do is to move on and find this piece of the puzzle. The integral from 1 to infinity, convert them to x's, which is this fella here, dx. Do you know the most common mistake people do in the midterm when I do a question like this, which I frequently do? They skip all of that and they just go to here. Because the only bit they remember is it's got an integral in it. So as long as I prove the integral part, I'm finished. If you don't have this bit, you haven't proved anything. So try not to be one of those people who do that. Now we tangent in space, that's a 12. I'll write that again. I'm thinking of what you do to it. It's x to the 12 plus 1. And someone went and said, can't remember who it was, but they deserve brownie points. I think it was Tom. That it's going to be a u sub, but the u sub is only x to the 6. So while I'm over here, and I convert that to the limit as t tends to infinity of 1 to t, that x to the 12 plus 1 becomes x to the 6 squared plus 1. Now you might not need that line, but I'm putting it in. And let's see what happens. If you differentiate with respect to x, you get 6x to the 5. If you then do the crossover, if you divide both sides by 6x to the 5, you isolate the dx. So I have the integral of x to the 5 over u squared plus 1 times 1 over 6x to the 5 du. And they cancel. And now we are looking at the limit as t tends to infinity of 1/6, because they cancel, 1/6, 1 over u squared plus 1. And I'm going to bring out the 1/6 just to make everything a little bit cleaner. Are you comfortable with where we are right now? The x to the 5's cancel and this 1/6. I'm just sucking out the integral just to get it out. Now this fella we can do, because this guy is an inverse tan. Well, it's an inverse tan of the variable u. But I like to return back to the x's. So it's 1/6 the inverse tan of x to the 6. And now we can evaluate it at x equals 1 to x equals t. To me, it just makes life easier if you return to the x's. Now, I should be able to figure out what's going to happen next. It's going to be 1/6 the tan of t to the power of 6. Take away 1/6 the inverse tan, almost forgot my inverses, of 1. Are we good? Now the next bit is going to be find out what happens when t goes infinite. I'm going to do brute force. It's going to be 1/6 the inverse tan. Infinity to the power of 6 is still infinite. Take away the angle that gives you a tangent of 1 is pi upon 4. So this is basically 1/6 of pi upon 4. You okay with the inverse tan of 1 being pi upon 4? Now, a lot of people, unfortunately, think that that's infinite because most of the time things like that are. But the inverse tan of infinity is not infinity. The inverse tan is a number, right? It represents an angle whose tangent is infinite. Now, you remember the tangent function shoots off to infinity? Do you remember what angle the tangent shoots off to plus infinity?
That's a 90-degree angle, right?
And in radians, because we have to work with radians, how much is that?
That is pi and a half.
Okay, so that guy is him. Take away 1/24th, because that's what that gets you. A 12th take away 24th, you now get, I don't know how surprising it is, but isn't that converging? And so that means our original, way back here, And if you could see the question, all there is two circles. One of them says converges and the other says diverges. And all you would do is put a dot there. So for 2 blinking pages of work, you get to do a dot. That's all you type. That's all you do. I can understand the temptation for you just to say, no, I'm just going to put a dot and go for it. But then you wouldn't have the experience of going through all the different nuances, all the different bits of algebra, the techniques for integrating, the tricks to find out if something's negative or not, all those little steps. You wouldn't have got any practice at them. And so you would be lacking, in a good way, you probably would be lacking at the end of it all. Has anyone got another one? I'm going to do 2 more. One from you and then one I'm picking. Has anybody got another one from that list that we zoomed through that you'd like to see? If that's too hard for you to remember, so it wasn't that. We shoot through them very quick. I'm going to shrink these up a little bit, that way we can see more at once. Here we go. -6 one, funny little fraction one, this guy, that guy, really weird decimal. That's the one I'm going to be doing, so don't pick 6. Weird looking square roots and fractional power one, that n squared plus 16 one, the weird n log one, this guy, and that's such. Any of those look interesting enough for us to do? I mean, I guess I could pick 2, but I'm definitely picking 1. Anybody got a preference?
How about the 3 over n natural log of n?
Okay, why not? It's a good question. There it is, number 9. Right, so that's going to be guy number 2. I wish this class was 12 weeks, because if it was, I could easily spend 3 days doing nothing but these, couldn't we? Because they take so long to go through. So I'm doing my best to kind of cover as many, things as I possibly can. So this is the guy that we're going to do. Does anybody know why this one starts at n equals 2 instead of the typical n equals 3 or 1, I should say? Why it
n
starts at
equal
2?
1, n equal 1 on the natural log of 1 will result in 2, 0, and 0 on the denominator doesn't mean anything.
Well, it would mean the thing's infinitely big, which would make this question really quick. So, does that affect anything? Not really. Can we cut some corners? Would you agree that as long as n is a reasonably big number, won't that fraction be positive? So we can say it's positive. If I now go for prove to me that you're negative, prove to me that the derivative is negative, that is not easy, right? There is no, to me, there's no obviously simple way to differentiate that. It's going to be ugly no matter how I do it. Okay, so this is just my brain. I'm not saying this is the good way of doing it, but it's how I'm going to do it. I'm going to call it that. That means I can differentiate it using the chain rule. So its derivative is going to be multiplied by the power, reduce the power by 1. That was the good part. Now the bad part. This thing in here is sometimes called the inside function. Don't I now have to differentiate by that? And this is a product rule because it's 2 things multiplied together. Great. So I'm going to put a little bracket here, change color for emphasis. I'll make that F, I'll make that G. And I have to find the derivative of the inside function by finding this guy. So it's -3. Might as well put that guy downstairs now. And this guy, what we got? We got a derivative, leave that guy alone. plus leave that guy alone and differentiate that, you get that. So I now have -3, the natural log of n plus 1, all over n natural log of n, all being squared. Are you comfortable about the derivative? Okay, now it's got 3 pieces, and n is going to be greater than or equal to at least 2, but there's a little wiggle room in there. So here goes. -3 is a number that's always negative. Would you agree something squared is always going to be positive? Now, as long as n is reasonably big, 2, 3, 4, 5, 6, would you agree that the log of n plus 1 eventually becomes positive? Isn't that combination negative then, so it decreases and we're done? So that's the step 1. Prove to me that it's positive and decreasing. And then the second step is find the answer to this integral. And we told you that it was going to be a substitution. And we also were told that the substitution was going to be log x, which isn't very obvious, but it is. So if you differentiate this guy with respect to x, you get 1 over x. If you do the little crossover thing, oh, right, you only need 3 lines, right? It's ready to go. So it's going to be the limit as t tends to infinity, the integral from 2 to t of 3 over x u times x du. So it's going to be the limit as t tends to infinity of, well, they cancel and basically you get the integral. Oops, those don't exist anymore. That guy. So it's going to be the limit as t tends to infinity of 3 natural log of u's, which then will turn into the limit as t tends to infinity of 3 the natural log of the natural log of x, which is a really weird function, starting at x equals 2 and finishing at x equals t. So it's going to be 3 times the natural log of the natural log of t, take away 3 times the natural log of the natural log of 2. Now, I'm not too concerned about numerical answers. I'm just concerned that it's a number. And I'm not too concerned about it being infinite, as long as it's just some kind of infinity, right? So, brute force coming up. Just pretty much what's happened in almost all these questions. Would you agree that that's just some ugly decimal that I could probably calculate, if I spent the time and effort, right? So I'm just going to pretend that, guys. Well, I'm not even going to pretend, I'm just not going to calculate. What's the natural log of infinity?
Infinity.
So isn't this going to be 3 times the natural log of infinity, take away some number? Would you agree that natural log of infinity is still infinite and 3 infinites is still infinite? Would you agree that this is infinity, take away a number? Would you agree taking away a number from infinity is not going to do much damage, even if the number's a weird decimal? So, conclusion, doesn't it diverge? Because its integral is infinite. And if it diverges, then doesn't, oops, wrong guy, doesn't this guy also diverge? We've only seen a few questions. Are you beginning to see the flow? Prove it's positive, prove it's decreasing by showing its derivative is negative. Find this infinite limit If you can get a number, it converges. If you get infinite, it diverges. See how this is going to fall. Right. Let's move to the one I chose. The only reason I kind of chose it is because it's different from all the others. Every single other question, I believe, gave you a formula, but not this one. Okay, that's the guy. Don't I need a formula for this fella? Okay. Now, would you agree it's 1 over something? Because they're all fractions, 1 over something. Even that one, if you call it 1 over 1. So the first answer is that. Second answer is that. Third answer is 1/9. Fourth answer is that one. What would the nth answer be if you continued with that pattern?
Is that 1 over n squared, right?
That's what I would say. And therefore, we now have our guy. So really, they've gave us an extra step. Didn't we have to create that from here so that we can now use the integral test? Are we good so far? Right. I'm going to cut some corners here. Would you agree that 1 over n squared is positive? As long as n is greater than or equal to 1, it definitely is. If I take this fella and I call him that guy, then I should be able to differentiate it by just simply using the power rule and then making it look pretty, right? Again, I'm doing this a little bit in the quick side, but it's a pretty easy function to prove. Would you agree that -2 is a number that's always negative? And would you agree that n cubed is positive, provided n is greater than or equal to 1? So that makes the derivative negative, and so it is decreasing. And we have finished step 1, even if it was a little bit rushed. Right? Prove to me it's positive and prove to me it's decreasing by showing that its derivative is negative. Now to finish it, I have to find what this guy is. Has anybody got a gut feeling? Is this going to converge, you think, or is this going to diverge? Any gut feelings? I mean, you have a 50-50 chance. If you're lucky, you'll get it right that way. Any gut feelings?
I think it diverges.
Okay. Anybody think it converges?
I think it converges.
Good. One of you is bound to be right then, right? So let's find out. That's going to be the limit as t tends to infinity of the integral from 1 to t of 1 over x squared dx. It's not the worst integral in the world. I won't need to do any clever math on this, but I do have to rewrite the 1 over x squared like that so I can use the power rule, right? So it's going to be the limit as t tends to infinity of add 1 to the power, divide by the new power. I kind of did one like this right at the start of today. That in turn has to be rewritten in that form because that's going to make it easier to work with. So we plug it in, it's going to be -1 over t minus plus 1 then. And I'm interested in what happens when t becomes infinite. I should be able to brute force it. And -1 over infinity is essentially 0, and 0 plus 1 gets you 1. And therefore, we now know that it converges. Are you good? Right. Now, at this point in time, we should be able to take any of the first, I think it's the first 9 questions. Yeah, the first, no, take it back, the first 12 questions, and basically test, does a series converge or does it diverge? And that's all we get, right? That's all we know. It converges or it don't. Wouldn't it be nice if there was a way of at least giving you an idea of roughly what it converges to, right? So I'm going to pick a guy, n equals 1 to infinity, 1 over n to the 4th. And you're just going to trust me, but that converges, right? So imagine we spent 15 minutes and we proved it, it converges, right? So we kind of bypass that. Now we want to know something. I want to know how many terms do you need to add to find the sum of this series correct to, and then we're going to insert whatever the number is, decimal places. So I want to know how many terms. Now, what do I mean by that? Right, if you just do one term, it's that, right? If you add 2 terms together, it's that. If you add 3 terms together, it's that. If you add 4 terms together, it's that, right? And so on. So the question is, how many of these do you need so that whatever that adds up to, you can be sure that when you round it off to whatever number of decimal places, that's essentially what the sum is going to be like, right? How many decimal places do you want? Justin, I'll put you in the spot. Pick a number and don't pick 82, because if you do, I'm going to let you do the question.
4.
4, okay. Pretty decent accuracy, would you agree? 4 decimal places. So if I come back and tell you that the answer is 1.2345, 2345, that's to 4 decimal places, that's pretty good, right? You know pretty much what the answers of the whole thing's going to add up to. And do you notice that when a series converges, that the values get small really quickly? Isn't that one of the reasons that they converge? So what that tells us in mathematics is that most of the answer to a series exists in the first, 5, 10, 20 terms. And if they get small really, really quickly, isn't most of the answer going to be in the first 4 or 5 terms even? And I think this one's going to be in the first 4 or 5 terms. That's what I think. That's just my gut feeling. So how do we do it? Well, got my little proof here. The integral from 1 to n, I just want to make sure I'm getting this right, because it is, yeah, see, I'm glad I checked. The integral from n to infinity, we're going to calculate that guy, right? And we're going to do it for 1 over x to the 4 dx. Now, if this guy from n to infinity, I want this guy to be correct to 4 decimal places. Now, if you round off a number to 4 decimal places, do you notice that I've done 4 zeros and a 5? Because when you round something up, isn't it the 5th decimal place that decides if you round it up or round it down? Right. So if you want 2 decimal places, you're going to do 0.005. If you want 12 decimal places, you're going to go 0.12 zeros and a 5. So all I'm going to do now is solve this problem. What does n have to be so that this integral is at least that number, right? That number or smaller, right? Because you're never going to get a perfect match, because isn't n going to be 2, 3, 4, 5, that kind of number? So it's going to be the limit as t tends to infinity of n to t, x to the -4 dx. And that's going to be the limit as t tends to infinity. Add 1 to the power and divide by the new power and evaluate it at x equals n to x equals t. And that's going to be 1 over 3x cubed evaluated at x equals n to x equals t. And that in turn is going to be the limit as t tends to infinity of -1 over 3 t cubed. Take away a takeaway, so plus a 1 over 3 n cubed. Now, if you make n infinite, brute force, in other words, you get this. And that's 0, so you now get this. Are you comfortable about where the 1 over 3 n cubed ends up coming from? Right, you have this limit, you plug infinity, you get -1 over 3 infinity cubed, which is just 1 over infinity, which is 0. And then you get this term, because taking away a negative makes an add. Now, this has to equal 0.00005. And I now have to try and solve this rather ugly equation. Okay. So if you do a little cross multiply thing, you get 0.00015 n cubed equals 1. N cubed then is 1 divided by all those guys. I have a calculator somewhere. There we go. 1 divided by 0.123015 ends up being 6, God, the devil's around here. 6666.67 or something. So won't n be the cube root of that number? So I'll take the answer, which is this guy, and I'll raise it to the power of 1/3. And the answer I get is about 18.8. More than I thought, but never mind. It's 18.8. You know you can't have 18.8 terms, agreed? So what do you think you should call the number of terms that you need? I thought you were going to get away with 4 or 5, but it looks like it's a lot more, isn't it? What do you need?
19.
You'd go 19. Suppose it's 18.03, because that can happen. What do you do?
Do I just make it become 18?
No, that's what normally you would think, wouldn't it? Round off to nearest. But don't we want to make sure that we got the accuracy that we're talking about? So basically always round up. Don't care if it's 18.8 or 18.08, everybody rounds up. So that means 19 terms. Now, if this question had came out with 3 or 4 terms, I would have actually just added them up and proved to you. Since it's 19, you're going to do the trust me, I'm a mathematician. If you add up from all of this, all the way up to 1 over, what would that be? 19 to the power of 4. Can you trust me? You would, whatever that answer is, it's what the sum would equal to 4 decimal places. We good? Right. You got time? Yes, we do. So, there's a name for this integral that I just wrote down wherever he is. Here he is here. This is called Rn. It's a remainder function. So there we go. Right, let's see if I can find one to do. They take someone. There we go. The last one. Perfect timing. We get this one done. Be happy. And they want it to be correct to 4 decimal places as well. And we don't need to prove that this converges in these questions. We'll assume that they do. So all we need to do is find our Rn guy, right, and remember to add 1 to it. Or at least round up, will do. So it's going to be the integral from 1, that I go and do it again, n to infinity. And the function is going to be x e to the negative 8x dx. And 4 decimal places is 0.0005. What technique will we use to integrate this guy?
Integration by part, right?
Agreed. And I'm calling that guy F and I'm calling that guy G. The UDV people can do their working using that notation. So what do we have? We have F capital G, take away the integral of F dashed capital G dx. That's what it looks like when you use that notation. So you have this fella and the integral of this. That's messy, because when you integrate e to the negative 8x, you get e to the negative 8x, and then this fella gets you a negative 1/8, not a times negative 8, but a times negative 1/8, because it's an integration. Take away, and the derivative of this guy is 1 with another one of these guys. And this becomes negative 1/8 x e to the negative 8x plus 1/8 e to the negative 8x dx. I'm just tidying that up. I can now just do the normal integration, which gets me another negative 1/8. So that's why that's now 64ths e to the negative 8x. And we will evaluate that at x equals n to x equals t. And we'll make the limit go from t to infinity. So it now becomes, well, I can tidy that up a little bit. It's always good to tidy things up, I think. So I can pull out, what can I pull out? I can pull out a negative 1/8 e to the negative 8x as a common factor. And if I do that, all I get is an x plus a 1/8. Oh, that's kind of nice. Right, so I'm
I
pulling
just
out.
had a quick question
Yes.
on the line above. So we took the derivative of 1/8 e to the negative 8x.
No, we integrated.
Oh, integrated. Yeah.
Yes. So
never
your
mind.
question?
Yeah.
Oh, we're good. Right. So it's going to be the limit as t tends to infinity of negative 1/8 e to the negative 8t, t plus an 8th. Takeaway, a takeaway is a plus 1/8 e to the negative 8n, n plus 1/8. Right. Plug in infinity here. You get negative 1/8 e to the negative infinity times infinity add 1/8. And then basically you don't get anything very interesting except to rewrite this expression here. I'm going to have to do a kind of cheat here. Can you trust me that this entire mess ends up being 0? Because if it doesn't end up being 0, then aren't we in trouble because it doesn't converge? Well, that do as an argument, so I don't need to do too much clever math in this because there is some messy math in this. Right, so we have now got that our Rn, the answer to this integral, ends up only being this fella here. And we have to find when is it equal to that guy. So I think that deserves a new piece of paper. When does this guy equal or better, meaning smaller, than 0.1, 2, 3, 4, and 5? If you are thinking, oh God, we're going to be here all night, trying to solve that by algebra is painful and I'm not even sure where to start. Good news, there's no way in the world I'm going to solve that by algebra. It's not doable by algebra. So we have to figure out an alternate method, right? I can tell you two methods. Here's the first one. You do n and you do the expression. And then you got your calculator and you set up y equals to be this guy. And it's going to be x's, but that's no big deal. I'm putting brackets around everything because I've had experience before where if you didn't put a bracket in, you end up with something different than what you thought you were calculating. You okay with that expression has now been typed into my one? Right. Table setup, blue button window. As long as this fella here says ask, it really doesn't matter what else is going on. So it is set up. I'm now going to go second table and clear out some old answers. And give me a guess, between 1 and 10, what do you think, how many terms do you think you might need? Give me a guess, 1 to 10.
5.
5, good a guess as any, right? 5 is 3 times 10 to the negative 18. Would you agree that's too much? That's more than 4 decimal places. Give me another number.
7.
Obviously, oh no, 5's too accurate. Don't you want less than 5? I should have said that, right?
Oh,
Far too accurate, right? That's more than I want, right? That's basically how accurate your answer is going to be. 18 decimal, well, maybe 17, right? So what do you want? Less than 5.
agree.
Okay, 5-3. Oh, I wasn't expecting this. Two. Oh God, no. 1. Wow. You only need to use the first number and your answer's good to pretty much 4 decimal places, would you agree? So what was the original one that we had? It was this guy. So if you want to do the series n e to the negative a10, right? Starting at 1 and going to infinity, you only need the first term. That guy. And whatever that comes to, it's good to 4 decimal places. So I'm interested to find out what that guy is equal to. So e to the negative 8. So the answer you get is 3.3546 and some stuff times 10 to the negative 4, which is 0.1234335. And if you round this guy off to 4 decimal, God, I'm going to have to do 5 or else the answer is no good. Essentially, the answer is 0.4003.